the problem with these commercial products is that they're very heavy and hard to maneuver, and as you can see, it has a very, very large geometry. So the overall purpose of our design is to kind of mitigate those, so we have a lightweight design. We'll be able to achieve less than half a pound with ours, and it comes to this smaller geometry, making it easier to maneuver on cool surfaces. From that, we also increase the suction pressure and suction rate, increasing overall efficiency of the pool vacuum system. And we overall reduce the lifetime cost, as you can see. So if the bristles were to break on this or start to wear away, you would have to buy the entire new system. But for ours, the bulk cost does come to $39.38. However, the cleaning tool attachment is replaceable. So the customer would only have to buy a new tool, which comes to $7.52, and they would just reattach it to the vacuum head.
This is our work breakdown structure. It's separated into management, mechanical, and testing. Within mechanical, we perform calculations to determine the angles of our prototypes. We created a drawing package, and then we constructed our prototypes. Within testing, it was separated into two categories. We did an initial vacuum pressure testing the first semester, and then this semester we performed cleaning efficiency.
Our mechanical requirements for our project consist of having universal hookups for both the pool hose and the telescopic pole that are universal to all pool assemblies. We will also implement a replaceable cleaning tool as to increase the longevity and decrease the lifetime cost of our product. We will also make sure that our design does not have a suction to the sides of pools or pool liners, because that will damage the pool itself. We also want to make sure that our design mitigates the amount of blockages that occur from different debris that you'll find in a pool. Next, we want to make sure that the weight is less than the commercial market head, which, like we said, is about 4 to 6 pounds. Ours, we want to be at least less than 1.5 pounds. Next, we want to make sure that our suction pressure at the head is about 50% higher than the 1 pound on the market. And finally, all the materials that we use in manufacturing our prototype have to be non-corrosive to water. Our mechanical specifications consist of manufacturing our prototype with 3D printing. The vacuum head itself will be made out of ABS, and the cleaning tool is made out of TPU, which mimics rubber. The vacuum head itself will have an interior angle of 33 degrees, which provided the best suction pressure without sticking to the sides of the pool. And also we have a structural wall surrounding our cleaning blade to make sure it does not fall off during use. The universal hookups will be for both the telescopic pole and the pool hose. The telescopic pole is about 1.25 inches, and the pool hose has both 1.5 inches and 1.25 inches diameter. The telescopic pole attachment itself will be made out of stainless steel because that is not corrosive in water. We will also make sure it is rigid, and that will reduce the weight of our product significantly. And finally, the magnets connecting both the head to the cleaning tool will be embedded in the 3D printing so they do not corrode over time.
Okay, so for the magnets we implemented into our design, the manufacturer provided a graph here. Figure 10 is a graph provided by the manufacturer for the pull force between any set of magnets. This one is specifically for the magnets we use. And the gap between the magnets within our prototype is 0.08 inches. The force between them is 0.64 pounds, and for our prototype it has 6 sets. So we have a total upward force of 3.84 pounds, and that counteracts the weight of the attachment itself, which is 0.04896 pounds. So it's significantly stronger than the weight of the attachment.
So we went through a couple iterations during our design process for our prototype. The next one, as you can see, we use the same angle as the one that he provided for us, just to make sure that our idea of having the magnets attached to the cleaning tool works, and as you can see, it did. So then we moved on to making changes to the interior angle to optimize the suction pressure, and we also made the pool hose attachment the one that we find on commercial heads. The next one, as you can see, all the way on the right here, has the same interior angle of 33 degrees. This one just has the extra wall on the outside, or around the rubber blade. And we also increased the thickness and length of the rubber blade itself. And the last change we made was to the telescopic pole, and we added an extra plate for stability to the design and also for ease of manufacturing.
So this is our final assembly for a prototype. The first part is a telescopic pole attachment. It has 2 screws attaching that to the vacuum head, and then the replaceable cleaning attachment connects to the vacuum head with magnets. In this drawing, you can see that the interior angle of our prototype is 33 degrees, and it has the little cavities here for the magnets. This is our rubber blade attachment. Last semester, it was just a straight wall up. We've incorporated a tapered design to increase the longevity of that product. And then our telescopic pole attachment, which has a wishbone clip to attach it to the telescopic poles.
So at the start of last semester, we noticed that there's a lack of research into the field for pool vacuum heads themselves. So we had to conduct our own analysis for fluid dynamic properties, which we found most beneficial for suction pressure, major loss, volumetric flow, and Reynolds, based on a varied angle for a sudden contraction. So once we concluded this calculation analysis, we came to the conclusion that the 45-degree angle for the interior angle would provide the most optimal solution for our problem. We likewise incorporated a kind of a testing point for the 33-degree angle, more so because it serves as a baseline as a medium. However, to give credit to Dr. Mari, it does come up within fluid systems a lot for this type of sudden contraction. So we also want to validate our results on that finding. From there, once we generated these 2 prototypes, we tested these against the prototype provided by Jim Lennox, which featured a 93-degree angle, as well as the commercial head, which we reference as a 180-degree angle. So from this, we were able to find that the 45-degree angle and the 33-degree angle provided the most consistent results for suction pressure based on a varied flow rate. So on the chart on the left, you can see for 45-degree angle is the topmost data points, followed by this is the 33-degree angle featured by the blue triangles, and then 93 degrees below that, and on the baseline for the commercial head, which provide the worst results. And we compared this to Reynolds to further quantify our results and verify the data. So overall, what we concluded from these results is that no matter what, if you decrease the angle within the sudden contraction, provide a higher suction pressure compared to that of the commercial head. With the 45-degree angle, we were able to increase the suction rate by 77% compared to the commercial head that we tested. And for the 33-degree prototype, we averaged a 52% increase. The next steps for our testing phase were to test how these prototypes operated by cleaning debris, in this case, which is sand. So we wanted to mimic as best as possible to a pool vacuum system as much as possible. So we would fill a bin with water and put sediment on the set area, which was the sand. To mimic the pool setting with sediment on the bottom, we would attach a prototype to 1 horsepower pool pump, and from there we turn on the system and record the time it took to clean up this debris. We varied the amount of debris by weight that we put on the bottom of the surface, and we would record the time that it took to clean it up. So this is the overall testing setup. On the video on the right, this is how we operated it. So into the pool pump and out into the return hose. So first we tested overall maneuverability of our prototype compared to that of the commercial head. As you can see from the video on the left, it takes a lot less time for our prototype to clean the corners, which is commonly found in pool systems, compared to that of the commercial head, where it took a couple tries to get into that corner, as it did push around the sediment rather than collect it right away. And here is just a better view of the before and after for this testing. So based on the sand collection we recorded the time, we put the sediment as spread evenly as possible on the flat surface of the bin, and we recorded the time it took to clean this set area. So here's the overall results collected from that data. So initially, when we first started the test, 45-degree angle honestly works too well. It sucked right to the bottom of the bin, and that then failed the requirement of not sticking to the bottom of the pool surface, ruining the line. So that shifted to our final design being towards the 33-degree angle. So we found that the 33-degree angle provided 33% less time to clean about half a square meter. And those are shown on the table on the right for those times. So it took on average 24 seconds for the 33-degree prototype to clean that area, and for the commercial head, it took about 29 seconds. For the chart on the left, it further quantifies the data to compare one square meter it would take. So it would take 48 seconds for a 33-degree angle, and it would take 57 seconds for the commercial head.
Here's our spring schedule. It has all of our important due dates and deadlines for this spring semester.
Here's our overall budget we spent at WOKES. So we accumulated $374.38. And compared to the real world budget, which came to $41,795, which the biggest component of that is labor cost.
For our ethics for this project, we wanted to, our big thing was safety, because working with pools, you have to worry about drowning. So we wanted to make sure that any part of our design will not harm people and or property. We also will make sure if danger does occur, that we will make design changes along with giving credit where credit is due, because the project idea was given by Jim Lennox.
So our future plans for this project is to test within a commercial setting, a residential setting in a pool. It was more so due to the lack of timing and the time of year that we tested our prototype, and we can test more varied degrees. We would also like to perform ANSYS Fluent simulations to further quantify our optimization at a higher rate compared to what we have done during the calculations for the semester. And we'd like to reduce overall single unit cost by manufacturing in bulk possible.
These are acknowledgements. Thank you to everyone that helped us along the way. These are our references. Any questions?
Yes, one thing I researched, there's quite a market opportunity for this type of product. The question I have is utility. The larger unit, the commercial unit, obviously covers more space, and the variance was 5 seconds in 1 year's time. But I was covering more space. I was picking up 1 degree or cleaning the pool fast. So what would be required, we had a slide there for cleaning 1 meter. Is yours optimal for cleaning 1 meter? The way product tried to verify that. I'm looking at the utility and the efficiency of the pool.
So that is why we tested overall maneuverability of our compared to our prototype and the commercial head. So the commercial head, yes, it does cover more area. However, it does push the sediment rather than automatically collect it. So with this larger area, it takes more time for that debris to get into it, whereas for our design with the commercial head, it goes straight into the intake.
Does it take more time if you're cleaning 1 area? You know, I'm talking about cleaning the whole.
Yes, so 1 square meter of the time it takes with the 33-degree angle is 48.62 seconds. And then with the 180 degrees, it is job, it improves the vacuum pressure and the cleaning efficiency of the tool. So future iterations of our project could increase the opening diameter. For our project, we wanted to keep as many variables constant as possible, so diameter was one of those variables. But future testing, along with ANSYS fluid simulations, would allow us to test larger diameters and different angles.
Okay, thank you.
Yes.
So that 180 degree, is it the commercial one?
Yes.
So it transitions from the flat to the hose opening at 180 degrees.
So that says 1 meter squared. So with the commercial one, there is fewer number of runs, I guess, but your design kind of more runs. What was the criteria for cleaning? Like, how did you define cleaning here? Because it's a function of how fast you are moving the thing. That I don't understand how come the 180 degree, which is much larger, takes longer.
Yeah, so unfortunately with pool vacuum heads in the market, their cleaning efficiency and their ratings basically are determined from users with the products for several months. With the timeline of our project, we are unable to do that. Ideally, we would have liked to. So we had to improvise some testing. That's where our variables came from, the suction pressure and the cleaning efficiency. Unfortunately, we weren't able to weigh the tub with the water and the sand before and after because that would have given us numbers to compare. So it was a visual test. To reduce any error within that, we performed several tests to make sure that our data was consistent.
And your time is looking 10 thousandths of a second? Like 48.6, like 57.041 per second?
So we only cleaned the half a square meter, so that was just from,
I know what is the measurement. Like, did you have that much accuracy in your measurement, like time is not like enough?
Just to understand the question, so you're asking like how many times?
The numbers, why is it so precise?
That was just more so because we calculated this, just to get more sort of a visual, here that on the chart on the right. So based on that calculation we provided, that was the output number. So as it,
That number you use a stopwatch, we put that number at the time.
yeah, so that's what we conducted with the experiment shown on the right.
So it's about like how fast you are to kind of press the kind of stop.
That's where.
yeah, we accounted for that error with the several tests. Unfortunately, like I said, there's no standardized way to test that, so we did anticipate that level of error and we tried to mitigate that as best as possible with our resources.
If there was stopping head on your design, the commercial one kind of pseudo, I guess,
Yeah.
or is kind of fixed angle?
Yeah.
Is it not a limitation?
Okay, so this one, because it's so, or the reason it is so heavy is because of the pin joint. With the pin joint, it allows the front of the head to pick up while you're trying to scrub the bottom of the pool floor, which makes it hard to use. So with ours, it's rigid. It makes it a lot easier to push along the floor without having to increase the weight of it, which is one of our requirements.
What is the role of those bristles that you did not include?
So the bristles are meant to agitate the debris on the pool floor. A problem with them is the way that they're oriented on the front. They push the debris ahead of the vacuum head instead of collecting it. So with ours, we have the squeegee blade, which will agitate the debris without pushing it in front of it. It will push it from the back and then collect it directly up into the
Which is
vacuum
still
hose.
kind of dislodge the debris from
Yes, that's the purpose of the squeegee.
And one last question. There is one slide about increased pressure, I guess 57% or something, with 33 and 45 degrees. Respect to the commercial one. Is increased pressure desirable?
So that based on the parameters that we set, because like I said, there's a lack of background research into these products in general, and just quantifying what would work best in that type of environment, we figured that suction vacuum pressure in general would be the best optimal way to quantify this data. So that was the variable that we're going off of. So the analysis proved that 45 degrees would provide that, based on the results of the test that verified it.
So
So realistically, what's the major debris in the pool?
So majorly, so there is some sediment that would.
I would assume like leaves or.
Yes, exactly.
Like how would that make a difference? Because I see the advantage of the commercial system when it comes to leaves and those people understand that. Why didn't you guys test that?
So we were donated the pool pump that we use in our testing, and since we did not pay for it, we had to go off of what they told us we were allowed to put through this pump because we did not have a filter attached to it. And sand was the most that we could put through it without ruining the pump since there was no filter. That's why ideally we would like to test with more, but the time constraints and the weather and stuff, pools aren't open to do that.
Could you go back to your slide 14? Oh, right here. So, sorry, this is slide 14. Okay. All right. So could you tell me like what those whiskers mean? Like, you have the data points, but you also have those whiskers. What are they?
So those are the error bars. So based on the amount of times that we.
I know what they are, but like how many samples do you use based on
We
to
did
get
four.
there?
Yeah, we did 4 each.
See, like normally, if you only have 4 to do a whisker, I mean that's you see that point, right? I mean that's gonna be because normally when you do that, that's essentially the range of the data distribution. You need a much bigger, much more sample to make it meaningful. Otherwise, you only have 4 samples. I mean the point of doing that becomes
Yeah, there was a major limitation with the suction rates that we were able to gather here because we had to vary the flow rate, and varying the flow rate didn't always vary the suction pressure a substantial amount that we were able to record. So that was just a limitation of our testing setup, unfortunately.
okay. Yeah, my point is that if you only have 4 samples, you just could do the simple average. You don't have to do the whisker. Okay.
Thank you.
Any more questions? No?
Alright, so I understand that the bristles of the initial design aren't necessarily effective at collecting all of the debris, but since it covers a larger area, and I would imagine when it agitates that debris, some of it disperses into the pool. Do you think you're compromising how much time you actually spend with your new design based on like a larger area? Because I understand it will collect it more efficiently, but if you're given 10 minutes with your new design, I feel it's going to cover less area, even if it cleans it better, whereas the initial design will probably cover a larger area, even if you only get like 7 to 8% actually.
Yeah, so with our maneuverability test, we were able to illustrate the fact that ours cleans a lot faster in the corners. Within a pool setting, you're also going to experience wrinkles within the pool lining that the bristles just simply, and the suction pressure of this prototype just simply cannot get at. So along the general flat pool floor, ours would ideally perform better. Again, we would like to test that in a pool setting, limitations due to the timeline of this course, unfortunately. Additionally, as I said earlier, if we had more time and the ability to run simulations, we'd be able to characterize the performance of a larger diameter head. So there is an opportunity to increase the diameter of that with still maintaining like the cone shape, which is really what increases the suction pressure of our product.